So this whole second section now is going to answer your questions of why in the world were we doing the things that we were doing. So we want to now actually develop a system for solving these systems of linear equations. And so we are going to want to know why we are doing certain operations and why we're doing it in certain orders. And we're trying to achieve certain forms of these matrices so that we can get to a solution. So if we looked, ooh, is this not going to work today? Okay, so we looked at these. We previously had looked at that example where we were doing all those different row operations on these set of equations in 3 variables. We had formed the augmented matrix. Then we had done some row operations on it. I didn't tell you why we were doing it in what order. But just know that we did row operations on that augmented matrix. We did skip the last 2 steps for the sake of time. So our resulting matrix did look like this one here in the bottom row. Please, though, do make sure that you go back to that example, that last example from section 1, because you're going to want to make sure that you follow along with all the calculations. You realize how to multiply a constant by a row and then add it to another row. So make sure you see how they did that math there. And so we did all that in order to get a solution for our set of linear equations. But now you're going to learn why did they do this in a certain order. So the next definition you're going to want to know is what in the world is a reduced row echelon form of a matrix, because that is what we were trying to achieve. We were trying to do a reduced row echelon form of the matrix. So here are its properties, and you will see what happens. So if we have a matrix, and if a row does not consist entirely of zeros, then that means the first non-zero number in a row needs to be a 1. So let's imagine a row, and let's look at it, and if it does not consist entirely of zeros, then that means the first non-zero number in that row needs to be a 1. So that is your first property. And so we're going to call that a leading 1. So you'll notice in those calculations we did before, we ended up with some leading 1s. If there are any rows that consist entirely of zeros, then guess what? We're going to put them down at the bottom. So if you have a whole row of zeros, they've got to be interchanged out and put at the bottom of your matrix. Then in that number 3, it says if any 2 successive rows that do not consist entirely of zeros, it means the leading 1 in the lower row will be further to the right. So if you notice in our matrix, the leading 1s started to become at a diagonal, right? So any leading 1 on a lower row needs to be further to the right. So we'll see what that looks like with some of these forms in a second. And then the other property that this reduced row echelon form has is that each column that contains a leading 1 has zeros everywhere else in that column. So you'll notice that some of the row operations that we did, we achieved some of that as well. Yes, tell me. What happens if you have 2 rows? You put them both at the bottom. If they have all zeros, they go down to the bottom of your matrix, because one of your elementary row operations is that you're allowed to interchange rows. So if you have rows of all zeros, you're going to interchange them and put them down at the bottom. Yes? What's a row of zeros even mean? Ah. What would that mean? How would a row of zeros correlate to an equation? Just like this. Yeah, you have a row of zeros would be 0x plus 0y plus 0z equals 0. So it's like there's no equation there. Yeah, so, or it got reduced to the point where it no longer illuminates any information. So that can also happen. It could be also, you might have a homogeneous solution or homogeneous system. So that is where it equals 0. So this is another slide to bookmark, either that or you want to go ahead and bookmark it in your text. You do want to know what are your properties of your reduced row echelon form. It's really super important. So let us look at these. This is going to kind of demonstrate the properties. So our property number 1 is If a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. So this is going to be the leading one. Okay, so it doesn't consist entirely of zeros, but the first non-zero number is going to be a 1. So here, this one was a 1. Here, all the rest of these were zeros, but then when it did show up, it was a 1. Same for this row, same for this row. What would you say about these?
There's a 2.
Yeah, there's a 2 there. So if a row does not consist entirely of zeros, then the first non-zero number in a row is a 1. Would this fit the definition?
No.
No. What about this one?
Yes.
Yes, it does. So it doesn't consist all of zeros. So the first non-zero number is a 1. Yes, that holds true for this row. Same thing for this one. That's a 1 here, and there's a 1 there. So you're going to see these matrices. You got to be able to recognize whether they have the properties or not. This one, your property number 2 is if there are any rows that consist entirely of zeros and they are grouped together at the bottom of the matrix. Does the first one fit that property? No, it does not. They left a whole second row of zeros. You can't do that. You got to put them down at the bottom. So here they went ahead and did that on this second one. They have all the zeros at the bottom. Okay, so here, 3. If any 2 successive rows that do not consist entirely of zeros, the leading 1 in the lower row occurs farther to the right than the leading 1 in the higher row. What about that first one? Yeah. So that third row needs to be interchanged with this one, doesn't it?
Yeah.
So here you have a leading, so just saying all of your leading 1s, if they're in a row lower, they need to be further to the right. So here's your leading 1 here. This one is out of order because your next leading 1 is in this position. So this needs to come up to the second row. What about that one?
Yes.
Yeah, that looks good.
It doesn't matter how much further to the right, just.
Right. Doesn't have to be the next spot. That's a very good point. Does not need to be the next spot. It just means the next non-zero entry, if in a row that doesn't have all zeros, whatever that first number is, it has to be a 1. But it doesn't necessarily have to go right in those spots sequentially. Could jump 1. Let's see. So next one looks pretty good. What about this one? Each column that contains a leading 1 has zeros everywhere else in that column. What do you think of this first matrix on the left? Yes.
Those 2 different matrices or the same matrix but exchange the order. They're 2 different matrices or it's the same number?
No, they're a different matrix because this one has a 1 here, and then this one has the 1 in a different spot. Yeah. So let's look at this one for that 4th property. Each column that contains a leading 1 has zeros everywhere else in that column. What do you think about this matrix on the left?
No.
What's wrong with it?
7.
So, all right, so we take it column by column. So this is the leading 1 for this row. Both of the other numbers in the column are 0. So this column is good.
The other 2.
This one, yeah, so here would be our next leading 1. What's wrong with this?
2
above it, right? You know, part of it's good. It was 0 below, but that 2 needs to be a 0. Then here you have your next leading 1. We got another problematic 7. That needs to be a 0. What do you guys think about the last one?
Yeah, that's it.
It looks good. It's okay about the last column because why?
Is it B?
Yeah, there is
Is it B column?
So as long as it satisfies those rules, it's okay. Here's our leading 1. All the rest of the stuff in that same column is 0. Same with this one. Same with this one. All of the rows that have non-zero entries that begin with a 1. This one is further to the right than the one above it. So it follows all the rules, even though it has that last column of all non-zeros and non-1s. Okay, so those you're going to want to make sure that you remember those rules. Those are going to be really important. So these are, so that, what we looked at was called what again? The ones that we just looked at with these 4 rules, those are called reduced row echelons. So it's very important to make sure that you're correct on your terminology and you know which one's which. So your reduced row echelon goes through all 4 of these properties, and you have to make sure that if you have a leading one, that you have zeros for the rest of your entries in that column. Okay, so it's this last property that's really, really important to make it the reduced row echelon form. Now, if you had decided to just stop at the first three properties, it would just be called row echelon form. It would not be the fully reduced. It would just be the row echelon. So there are many different matrices many different forms of a row echelon that you can have, because it might depend on how you did your different row operations. However, that final reduced row echelon form is always going to be the same, no matter how you got to it, that final reduced row echelon form. However, you might have various row echelon forms to get to that point. So here's just to kind of show you the difference. So here is the reduced row echelon form. Here you got leading row of 1. It's the furthest to the left for the first row. It has zeros all below it. Here, your next leading number here is in the next spot, further to the right. Everything in that column besides this entry is a 0. Same with this one. All the rest are 0. This leading one is further to the right than this one or that one. So this is in reduced row echelon form. Here, what do you notice is different about that one?
He doesn't allow numbers to be in the same column.
Right. So you have you've reduced it so that it has all its leading ones. However, you did not do the additional fourth step where everything else in the column is also is a 0. So here you got 4 still left in the second column. Here you still have a 6 and a -3. So this one is your row echelon form where you have done enough operations such that you have all your leading ones, but you have not done that extra fourth step where you are now making sure that there is zeros in the other spots in the column. Yes.
Would that still work to find like X, Y, and Z?
This one?
Yeah.
It can. A lot of times, so that's part of your section 2 as well, because you don't necessarily have, so the best way to kind of solve problems is to kind of get to this reduced row echelon form, because you reduce that matrix as simple as it can get. However, for the sake of time, or maybe you don't really need to, maybe all you do is you go to the row echelon form and then you back substitute. So here we reduced this enough. We didn't get to the full reduced row echelon form, but we got to enough that we know what C equals. So we solved it enough where we know, okay, C equals 5. Then that's enough for us to go ahead and put back in the other equations, because then if we know what Z is, we can put it in this spot. We can solve for Y as well, right? Then we know Y and Z, we put those in the top one, and we can solve that one. So not very good. So not in every instance, you need to do the full out. If you're able to get to this point and you've got it simplified just enough here, you can back substitute in, then you can do it that way. What form of a matrix is this? Reduced row echelon, right? What's cool about this?
Gives you all the answers.
Gives you all the answers. So here's why you would want to do it, right? You get through all those row operations, boom, 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 boom. You know what all of your different variables equal. So here, just wanted you to realize definition. This is an important definition. If a linear system has infinitely many solutions, then a set of parametric equations from which all solutions can be obtained by assigning numerical values to the parameters is called a general solution of the system. So I want you to look at that. We're going to talk about that next time because we're going to be writing parametric solutions. But do make sure that you keep a running tally of your definitions. So we'll get that. Okay, so I did want to get to the reasons why we're doing stuff. So as I showed you before, one of the benefits of doing that reduced row echelon form is you can get to all the values of your variables. But here is the actual step-by-step of what it is that we're doing. So somebody mentioned it before. We are doing Gauss-Jordan elimination in order to get to a reduced row echelon form. So here, this is where we are going to strategically pick what operations we're going to do in what order to get to that reduced row echelon form. And so there's a method to do this. So we have to keep in mind, what are our reduced row echelon properties, right? So what we're going to be doing is we're going to be going down the matrix and doing operations. That's going to be the Gaussian part of the reduced row echelon elimination. Then once we get down to the bottom, we're going to go back up the matrix and do that fourth property and get rid of all the numbers and turn them into zeros. So going down, you're establishing all of your leading ones. Once you have all like your leading ones, Then we're going to go back up the matrix and get rid of all the zeros in their columns. Does that kind of make sense? So we got to go down first, and then we get to come back up. So the Gauss step is down, and then your Jordan is going to be going back up. So it's kind of a two-step kind of thing here. So just if I were to ask you guys, you were faced with this matrix and you know the properties of your reduced row echelon form, what row operation might you want to do on this matrix? Because remember, what do we got to get? We've got to have a set of leading ones, right?
I
Yes.
think the second row would have to be put at the top and then multiply everything by 1.5.
Yeah. So to get to what leading one starting in this spot, or the furthest left that we can get, well, this first row is these first row of numbers is not going to get us there, is it? It's out of place. So we got to move that row. So we get to do a row operation and interchange some rows. So you're going to want to think to yourself, okay, what is your leftmost non-zero column? That's obviously going to be that first column there. We got some couple contenders here. So here, the first thing you would want to do is you might want to interchange some rows. Now, here is where you're faced with a choice. Yes?
Could use it to change first and third row.
You could. Yeah. So that's the interesting thing. You could have moved this row up to the top, or you could have moved that row up to the top. So here's an important rule. Depending on how you guys decide to do these row operations, you guys might have different versions of your row echelon form. So your intermediary matrices might look very different from what operations you choose, or which rows you started off with that you interchanged. However, at the very end, everyone should end up with the same reduced row echelon form. But the row echelon matrices that you create on the way there could be different from one another. Does that kind of make sense? Depending on what steps you decide to choose. Some of us will be able to combine steps easily. Some of us will choose more wisely than others. Some will have to, might do a little bit more work. But at the end of the day, whatever way you got there, you should all end up with the same reduced row echelon form, which has all four of those properties. So keep that in mind. So here, we'll just go with what they did. They went ahead and did the first and second rows. They decided to interchange those. Okay, so we've interchanged those. Then what do we got to do? What we want to start, we got to go down our matrix, right? So we need to make that first row a leading one. What do we got to do? We got to multiply, because that's one of our row operations that's allowed. We got to multiply that first row by half to get that one leading one in this spot. So that should occur to you, right? How do I make that a leading one row? So here we did it by 1/2. Let's see. Oh, just online students, I'm not writing anything on the board. I'm writing on the slide, so you didn't miss anything. If you hear my voice going in and out, it's because I'm just walking around. So you're not missing anything. Okay, so we did that by multiply by half to get that leading one. So now what would you do? So now to have that be a leading one, you need to get zeros below it. That's going to be one of the things that we need to do to have that be that leading one. So we have to do -2 times the first row, and then you're going to add it to the third row. So does everybody see? Let me get my pen out here. So everybody sees, does anybody have any issues with that calculation there? So we did, this row is going to be -2 times it, and then it gets added to that third row. So -2 times 1 is -2 plus 2. Then that's going to lead here to that 0. Then we got -2 times 2. That's going to be -4 plus 4. That's going to be the 0 spot. And so on and so forth. Does anybody need to be explained how those calculations go? What we're doing?
There's no particular order to do this.
Yes.
So you could have started off by multiplying the top one by -1 and then adding it to the bottom one.
No, so there is an order where we're trying to establish where the leading ones is. So for this one, we did have to establish that one of the rows had to start with an actual number, not a 0, to get that leading one. So that's part of it. Yeah, so here was our original. This is never going to be helpful to start off with the zeros. We have to get a leading one in that spot. So we either choose this row or this row to interchange with it and start all our reductions. So that's what I'm saying. You could have, you had a decision tree here. You could have chosen the bottom row or the second row to interchange. But we're still trying to do systematically create that leading one. So we decided to do the first and second rows are interchanged. So now that we decided this, now we did the first row, we multiplied that by a half. So everybody sees where we get that matrix? Okay, so now to have that be an official leading one, we need to have zeros underneath it. So we need to do matrix operations so that we get rid of that too, because otherwise we won't have a leading one. So the best thing to do would be to multiply that first row and then add it to the third. So now we have this resulting matrix. So does anybody, yes, go ahead.
The second row has a zero, the second, I think we'll also have to submit the future to the third one. Couldn't we just do it now, solve it as defined by the person and the second one?
Yeah, so that's what I'm saying. Like, people will get to things in a different way. But what is overall kept consistent is that we're trying to create those leading ones so that we can get to our final reduced row echelon definition. So like I said, how you might do it might be slightly different than the way another person might do it. As long as you're doing legitimate row operations, you have a couple different options. Yeah.
In a case where like there's not already a zero like in the column underneath
Yeah.
one of the ones, is the only way to get a zero by doing the
Mhm.
operation where you multiply by row?
And then add it. That's how you get a zero. You're exactly right. So this is where you have to be strategic. If you already have rows that have zeros, those can be very helpful to you. Then the ones that do not have zeros, you're going to have to create it by doing the row operation, like you said, multiplying a certain row by a constant and then adding it to another row so that it then becomes zero. So you're going to have to strategically create these things. So this one, we have now created in that third row some zeros by strategically doing that. So now that top row, we don't have to consider anymore because it's got its leading one. So now we're going to be concerning ourselves with the next two rows. So what do you guys think with these? So in the blue, we're not going to worry about right now because that's kind of set for now. It's got its leading one. Everything below it is zero. So now what do we got to do? We got to create the next leading one, right? By our definitions, where should it go? It needs to go further to the right than this first one, right? So these are kind of, we know that there's not going to be a leading one in this spot because these are zeros right here. But we're going to have to create it with these rows. So as it is right now, which one do you want to do? Here's where you could, switch the rows again. But in this case, they went ahead and multiplied by a negative 1/2 to get that one. You guys see that?
So it doesn't have to be directly the next column?
Yeah, like what we could have done is we could have switched these rows with 1 on 5 was on top, and then we divided by 1/5.
Yeah.
See, so that's what I'm saying. Like there are different ways to do it, but you do have to create that next leading spot.
And you can only multiply to get that one. You can't like add 1 to 0.
No, because then you get a zero.
Exactly.
Right. So you got to do the row operation where you're multiplying a row by a constant only as your operation in order to get that one. So now we're creating our next right leading one. So we've done that. So how would we get rid of that 5? Because if it were this to be the next leading one, it needs to have a 0 underneath the 1, right? So what are we going to do? I heard we're adding which two? No, the first one we're not going to consider. Yeah, you're going to multiply that second one by 5. You're going to take use of those zeros there. You're going to multiply that second row by what? -5, and then add it to the third. So if we go ahead and do that, now you get rid of that 5. And then you're going to have some fractions. So you are going to have to deal with some fractions. So now it's looking pretty good. So here we created our next leading one here. We've got a 0 below it. So we turned that 5 into a 0. Now what are we going to do? Yeah. So now we're moving on down. So we have now 2 rows that are now taken care of. They have their leading ones with zeros below it. Now we just need to figure out how to get that leading one in that next row, right? So we just have the third row left. So what are we gonna do with that one? Yeah. So we're going to multiply that by 2. So now all of them have a leading 1. So don't forget, it has to meet that definition. If you have a non-zero entry, the first one has to be a 1. You look at your reduced row echelon rules. So now we have 3 leading 1s. So we've gone all the way down the matrix. We've created all of our leading 1s. So now what do we got to do? We got to go back up, and we have to make it fully reduced row echelon. Because now when we go back up, what are we doing?
Making it to 0.
Yeah, you got to make the rest of the numbers in your leading 1 column zeros. Now we're just going to be going back up. So here we're left with this matrix. And so now we're going to get into a different form here. So for this first step, we're going to be doing 7/2 times the third row and add it to the second row. So why are we doing that? Yeah, we want to get rid of this weird negative 7/2. So we multiply that bottom row by 7/2 and add it to the second row. So that now, this 7/2 now has a 0 sitting in front of it. Okay, so we see where we got that? All right, the next thing, okay. Well, what's the next problem we have? We got rid of that 7/2.
You can times the second row by 5 and then add it to the first. To get rid of 5.
Yeah, so here's where like, but you do want to try to go like kind of up. Yeah, you want to kind of be a little bit systematic about it here. So what is the next one that they did? They took care of the next 0, right? So the next 0 that we got to get to is this in this position. So they basically they did what? They multiplied the third row by -6, added it to the first. So now we're looking good. So now we've got this whole row done, or sorry, this whole column done, right? We've got our leading 1. We've got everything else in that column is now a 0. So now we kind of keep on going. Do we need to worry about this column?
No,
Why not?
because it doesn't have a 1.
Yeah, we don't have a leading 1 in that one, right? Yes, go ahead.
When we multiply the 6 by the second row, no, by the third row, and adding to the first one, why do we only apply to the 6 and the 14? Like the 2, the -5, and the 3 stay the same.
Yeah, because -6 times 0 is 0. Then adding 0
Oh, well, then,
to your first row doesn't change anything. Yeah. So that's why you want to go, it makes it much easier if you start here and work up systematically when you go back up. Yes.
So the column with only the 3 is fine as it is, or does that need to be?
Yeah, that doesn't need to have anything done to it, right?
Okay.
Yes.
That also hold true for the column that only has the 2 then?
Yes.
Okay.
So now we got to go. So what is the next column then that we got to worry about, right? It's going to be that one that has our next leading 1 in it, right? So what are we going to do? Yeah, we're going to do 5 times that second row and add it to the first row. So now we got that 0 above that 1 we wanted. So this is the one that we took care of. Okay, we got one more step here. Oop. No, wait, no, we don't. We are done. Did we get it all the way to reduced row echelon form?
Yes.
Yes, we did. So now what happens?
I can X the Y and C for.
You should be able to now solve all that because now you have the values for things. So this is as simple as this matrix could get. So you're going to have to use these. So we've got 1, 2, 3, 4, 5. The fifth variable is going to equal this. Our third variable is going to equal that one. And then we're going to have to set up an equation where these are related and we substitute these in. And we'll get to that next time. So that is the whole point of it. So please review your elementary row operations. Please review your Gaussian elimination. So remember, Gauss goes down, and then we're going to do our Jordan on the way back up.